All right, guys, so we are now going to go over some of these practice problems. So I went ahead and labeled some of these as challenging problems. So for those of you who feel like you're maybe struggling with some of these topics, skip the challenge questions until the very end and come back. But for the sake of this video, I'm just going to go through it chronologically, but feel free to skip the challenges or skip this part of the video when we're doing these challenge problems to come back to it. So to get the most out of this video, you really need to utilize the pause button, okay? So I'm going to stress to pause this video before we tackle each problem, and I want you to try it on your own first. When you get stuck, you can hit play, or whenever you want to check your work, you can hit play. But for the most part, I just want you to take the opportunity to pause this video so that you can try these problems on your own. So, because again, you're only going to get better at this stuff when you do it yourself, okay? So let's go ahead and start with number one. So number one reads, if 30 grams of the hydrocarbon, so the hydrocarbon here, we're referring to C4H6O2, reacts with excess oxygen, and that's oxygen gas, how many grams of CO2 are produced, okay? So it may be beneficial for us to just write out, well, where are we going and where are we starting and where are we going? So we're starting with 30 grams of the hydrocarbon and we're going to grams of CO2. Okay, next, we should always balance our reaction first. So to balance our reaction, I'm going to zoom in here. To balance our reaction, we want to find elements that are in only one reactant and one product. So we have 4 carbons in this reactant, none in this one. So that's a good candidate. Only 1 in this one and none in this one. So carbon is our first good candidate. So we have 4 carbons on this side and 1 on this side. So in order for us to balance, I need to have a 4 here. All right, so our carbons are balanced. Now our hydrogens is 6. And we have 2 hydrogens on this side. So how many hydrogens are we going to need? Or what coefficient are we going to need in front of that water? 3, exactly, 3. So we have 4, 3, and our carbons and hydrogens are balanced. Now let's go ahead and do our oxygens. So on our right side, we have 4 times 2, which is 8 oxygen, and 3 times 1, which is 3. So we have 11 oxygen total on our right side. On our left side, we have 4, but we're going to subtract 2 from here. So we need to have 9 more remaining. So I need to get 9 oxygen out of this O2. The only way to do that is to do a fraction, because 9 halves times 2 is equal to 9. So I'm going to put a 9 halves here. And we can't have half, so I have to multiply every term here by 2 in order for us to cancel that out. So it's 2, 9, 8, 6. So this is now balanced. If you don't believe me, check the work, okay? So now that we have our balanced reaction, let's go ahead and try the problem. So pause now if you'd like to try number 1 on your own. Okay, welcome back. So we got 30 grams of C4H6O2. And in order for us to go to the other side to get how many grams of CO2, I need to go from grams to moles. So to go from grams to moles, I'm going to need to figure out the molecular weight of C4H6. So I have 4 carbons, 6 hydrogens, and 2 oxygens. So 4 carbons, that's 4 times 12 grams per mole. Again, we get this from the periodic table. 6 times 1 gram per mole, and 2 times 16 grams per mole, which gives us 48, 6, and 32. And that's going to give us a total sorry, I forgot my calculator. Total of 48 plus 6 plus 32 gives us a total of 86 grams of C4H6O2. Now, ask yourself, why are we dividing by grams? Right? It's because we're canceling it out. We want to get to moles so that we can get onto the mole train. Okay, so this next step is the key step. This is our Stoich step. Okay, so this is our Stoich step. So our Stoich step, we use our stoichiometric coefficients. This is the only time where they come in handy. We're not using oxygen because it's in excess, and we're not using water because we don't care. We only want to know how many grams of CO2. So for every 2 moles of C4H6O2, we form 8 moles of CO2. Okay, so now we stoiched over to the product side, and more specifically to how many moles of CO2. Now we're going to go from moles to grams of CO2. So if you don't remember how to do this, well, actually, we just did it, right? Equals 86 grams per mole, right? We did this because we calculated the grams to mole ratio of our hydrocarbon. Now we're just going to do the same with CO2. So do the exact same process with CO2, and you should get, for every 1 mole of CO2, we get 44 grams of CO2. So our answer should be 30 times 8 times 44 divided by 86 times 2 gives us 61.4 grams of CO2 produced. All right, next one. If the density of CO2 is 1,580 grams per cubic meter, how many liters of CO2 are produced from 52 grams of the hydrocarbon with excess oxygen? Okay, again, if you're looking at this problem as a whole, you may be freaking out. Let's take it one step at a time. Where do we start? Well, we were told we start with 52 grams of the hydrocarbon, so that's a good place to start. All right, and we already know the mass calculation for C4H6. Okay, and we're trying to go to density of CO2. Well, if you notice, CO2, there's a gram value here. So I'm going to get to grams of CO2 doing almost the exact same process. So if you're a little confused about why I'm doing this, just review the last problem. Or sorry, problem 1, if you're jumping back to this from later. All right, and then for every 1 mole of CO2, we get 44 grams. Okay, so we got into grams of CO2. Now that we're in grams of CO2, we can use this ratio to get cubic meters, and those cubic meters can tell us how many liters, okay? So we need 1,580 grams of CO2 that are in every 1 cubic meter, and for every 1 cubic meter, there's 1,000 liters. Enter. So let's do this calculation. 52 times 8 times 44 times 1,000. And we're going to divide that by 86 times 2 times 1580 gives us 67.35 liters of CO2 gas produced. Okay? All right, so the key with these problems, especially the challenge problems, stay organized, right? Stay organized, know where you're starting, know what you're trying to get to, and just do one ratio at a time. Okay, if you react 50 grams of the hydrocarbon with 50 grams of oxygen gas, how many grams of water are produced, okay? So with this one, I gave you 2 known quantities. I gave you 50 grams of C4H6O2 and 50 grams of oxygen gas. And then to do this, we need to stoich over to the same product. So in this case, we're going to water. So let's calculate how many grams of water we're going to form from each of these reactants. And then from there, we're going to choose the one that produces the least amount of water, because that is the one that is our limiting reactant. That is what is bottlenecking our reaction. So we already did these calculations, so I'm not going to dwell too much on them. So for every 2 moles of C4H6O2, we form 6 moles of water. form 18 grams. We're going to do the exact same process. I'll hit enter in just a minute. Exact same process with oxygen. One oxygen atom weighs 16, so two of them weighs 32. And then we go back up to our equation. For every 9, I should actually erase these. So for every 9 oxygen atoms, we form 6 H2O. Again, we're going to grams, so it's the same step here. For every 1 mole of H2O, we have 18 grams of water. So let's finish this up. 50 times 6 times 18. Divide that by 86 times 2, which gives us 31.4 grams of H2O. And then let's do the second one. 50 times 6 times 18. Divided by 32 times 9. Gives us 18.75 grams of H2O. So the one that we're actually going to be working with is going to be oxygen. So this is our correct answer. 18.75 grams of water. Our limiting reactant was oxygen because it produced fewer molecules of water. Sorry, fewer grams of water, hence fewer molecules. Okay, how many grams of product are formed from 30 grams of the hydrocarbon with excess oxygen? So excess oxygen means ignore, right? We don't need to think about oxygen. So in this case, we actually still kind of need to do two different reactions because we need to figure out, well, how much does 30 grams of CH4 produce? Right? How much of each molecule? So we got to do two different questions, two different equations. So for every 86 grams of C4H6O2, we form 1 mole of C4H6O2. And then for every 2 moles of C4H6O2, we want to go to both products in both equations. So we need to go to CO2 and to water. So I'm just going to make this one CO2. So CO2 was 8 moles of CO2. And then for every 1 mole of CO2, we form 44 grams of CO2. Okay, we'll calculate that in a minute. So same step here, 86. And then for every 2 moles of C4H6O2, we would form 6 moles of water. And again, because we want to know the total mass of all of our products, how many grams of product, we need to do both of our products, not just one. So 1 mole of H2O produces 18 grams of water. What are you doing, kitties? Okay, so we get 30 times 8 times 44. Divide that by 86 and divide that by 2. So we get 61.4 grams of CO2. And we get 30 times 6 times 18. Divide that by 86 times 2, which gives us 18.8 grams of H2O. So now we just need to add them together. So 61.4 plus 18.8 gives us a total of 80.2 grams of products, right? Both. Ooh, kitties. You all right? What happened? How did you jump like that? All right, well, that's exciting. Okay, next problem. So this one was the reaction we did in our lab. So the reaction above is the same reaction that we conducted in our lab. If you conducted the same experiment but attached a balloon mechanism to collect all carbon dioxide, how many grams of CO2 would be produced from 0.25 grams of baking soda and 3 grams of HCl? So whenever I don't tell you that one of the reactants is in excess, that means you're going to have to do two different problems because it's a limiting reagent problem. So 0.25 grams of NaHCO3. Each of these molecules, I believe, is 24. So let's go ahead and weigh them out here. 23 grams per mole. Hydrogen is 1 gram per mole. Carbon is 12 grams per mole. And oxygen, but we have 3 of them, is going to be 48 grams per mole. So add them all up. 48 plus 12 plus 1 plus 23 gives us 84 grams of baking soda per mole. And then we got a Stoich over. So if you, sorry, I kind of jumped the gun. We should have balanced it first, but this is actually already balanced. Just double check. For every 1 mole of NaHCO3, we form 1 mole of CO2. And then we already know this next step. For every 1 mole of CO2, we form 44 grams of CO2. And we'll do the next one for 3 grams of HCl. Chlorine is 35.45. So that's 36.45 grams of HCl per 1 mole of HCl. For every 1 mole of HCl, we form 1 mole of CO2. This is our Stoich step, right? So from every 1 mole here, so the stoichiometric coefficients for both of these is just 1. For every 1 mole of CO2, we produce 44 grams. You can probably already tell which one's which, or which one's going to be our limiting, but let's just go through it together. 0.25 times 44 divided by 84 gives us 0.13 grams of CO2. And then the one below, 3 times 44 divided by 36.45 gives us a whopping 3.6 grams of CO2. So which one's limiting? 0.31 grams or 3.6? Right? Correct. 0.13 because it's less, right? It's forming less. So our limiting reagent is baking soda. And we would form 0.13 grams of CO2. So that's our final answer. Now, I recommend just putting a line through this so you don't get too confused. But you can also show your work. But if you don't want to do that, that's fine. Just leave it as is and box the correct answer. All right. How many moles are produced from excess HCl and 2 grams of baking soda? So if I ask for moles or I give you moles, we're in a much better position because going from grams to grams takes the longest. Also, excess is me being nice. So we got 2 grams of NaHCO3. And then for every 86 grams of NaHCO3, we form 1 mole of NaHCO3. And then for every 1 mole of NaHCO3, we form 1 mole of CO2. Or sorry, we're going to water, not H2O. 1 mole of water. Again, this ratio is a 1-to-1 because all of our stoichiometric coefficients are implied ones. There's no balancing because it's already balanced. Okay, so that's our Stoich step. So we form 1 mole. Now we're done because I just asked for how many moles of water. We're in moles of water, so let's calculate. 2 divided by 86 gives us 0.23 moles. Sorry, 0.23. 0.23 moles of H2O. That's it. All right, not too shabby. How many grams of water are produced from excess HCl and 2.9 moles of baking soda? So similar. We're starting with moles, 2.9 moles of NaHCO3. And then we're already in moles, so we have the ticket to get on the mole train. So we're going from here to water. So it's a 1-to-1 ratio. So for every 1 mole of NaHCO3, we form 1 mole of NaHCO3. Oops, sorry. Water. For every 1 mole of water, we form 18 grams. Let's do it. 2.9 times 18. Divide that by 1, so it's just 52.2 grams of H2O. All right, number 4. How many grams of NaCl would be produced from 3 grams and 13.2 grams of baking soda? Okay, so this one is a limiting reagent because I did not tell you which one was in excess. So 3 grams of HCl. HCl is 36.45. Oh, wait, didn't we just do this? Yeah, we did. So let's just take that number. So I'm going to do, because I have the power of the iPad. Copy. Paste. But then we got to change this one and this step. Okay. So we're going over to NaCl. So for every 1 mole of HCl, we produce 1 mole of NaCl. And for every 1 mole of NaCl, we produce 23 plus 35.45, which gives us 58.45 grams of NaCl. So 3 times 58.45, divide that by 36.45, gives us a total of 4.81 grams of NaCl. But that's if HCl was our limiting reactant, so we got 1 more to go. 13.2 grams of baking soda, NaHCO3. Divide that by 86 grams of NaHCO3 for 1 mole of NaHCO3. And again, because all of our stoichiometric coefficients are 1-to-1, it's just going to be a 1-to-1. 1 mole of NaHCO3 for every 1 mole of NaCl. You may be wondering, well, why do we have to show this step if it's a 1-to-1? Because 1 divided by 1 is just 1. And it doesn't change our number. Well, because it shows me that you understand that you're doing stoichiometry. So you got to show it. You got to show your work. So 1 mole NaCl forms the 58.45 grams of NaCl. So 13.2 times 58.45. Divide that by 86. Gives us 8.97 grams of NaCl. So my question to you is, which one's limiting? If you guessed HCl, you were correct. HCl is correct because it produces less product. So it's 4.81 grams. HCl is our limiting reactant. All right, next question. How many moles of atoms of NaCl would theoretically be produced from 2 moles of baking soda and 3 moles of HCl? So this one's a toughie. Okay, so it's tough conceptually, but it's actually pretty simple mathematically. So I'm going to go ahead and do both. 2 moles of NaHCO3 and 3 moles HCl for every 1 mole. Oh, we're already on the mole train. So for every 1 mole of NaHCO3, we produce 1 mole of NaCl. Again, it's a 1-to-1. Our equation is balanced at a 1-to-1 ratio. And then for every 1 mole of NaCl, we form how many moles of atoms? The question is, how many atoms are in NaCl? 2. So 2 moles of atoms. Hey, kitty. All right, same step here. 3 moles of HCl for every 1 mole of NaHCO3. Oh, sorry. I'm off my game today. HCl, 1 mole of NaCl. And for every 1 mole NaCl, we form 2 moles of atoms. Okay, so 2 moles times 2 is 4 moles of atoms. And then here it'd be 3, so we get 6 moles of atoms. So again, which one's correct? We have 2 different answers. So which one's limiting? If you guessed baking soda, you are correct. So the correct answer is 4 moles of NaCl. This is why it's important to show your work, and I'll explain why. If you were to put 6 moles of 6 moles of atoms here, thinking that it was this one instead, that's a very honest mistake. And if I saw your work, that's awesome, right? I would give you 3/4 of the points for this problem because you just missed the limiting reactant. That's no big deal. But if you just put 6 moles of atoms and nothing else, you missed the answer. So therefore, if you have no work, I have to assume that you didn't know what you were doing or you didn't show your work. So then you miss all the points. Okay. So it's very important. You can either get 3/4 of the points, 75% of the points for this problem, and just guess the wrong one or 6 moles or whatever, or miss all the points. So it's up to you. All right, last page. So this is a Haber process, which is pretty cool. I think it was done in the early 1900s. Did a lot of incredible things in terms of modern day agriculture. So I'm going to give you a second to balance it out. So go ahead and pause the video if you need time to balance. All right, if you're back, that means you balanced it. So you should have gotten 3 and 2. Okay, 3 and 2. So the first question is, all this nonsense, you don't need any of this. If a farmer needs 1 kilogram of ammonia, how many grams of nitrogen gas does she need? Well, hold on a second. We're going backwards because I gave you the amount of ammonia, but I'm asking you to go back to the grams of nitrogen. Well, that's totally fine. We have a system in place to do this. We have stoichiometry. So the first things we need to do is convert out of kilograms to get into grams because our molecular weight is done in grams per mole. So let's first get to grams. So for every 1 kilogram, we have 1,000 grams. Now, for ammonia, for every 17 grams of NH3, we got that because nitrogen weighs 14 and every hydrogen is 1. So 14 plus 3 is 17. We get 1 mole of ammonia. And now we're on the mole train. So let's go back. So 1 mole, for every 2 moles of ammonia, and we got that 2 moles from this number here. For 2 moles of ammonia, we need to form 1 mole of N2. And we need to figure out how many grams, not how many moles. So for every 1 mole of N2, we form 28 grams of N2 gas. So this is going to be 1,000 times 28. Divide that by 17 times 2. Gives us a total of 823.5 grams of nitrogen gas in order to give the farmer 1 kilogram of ammonia. Okay. Next problem. How many moles of ammonia are produced from 30 grams of nitrogen and 45 grams of hydrogen gas? Well, neither of them are excess, so we have to determine which one's limiting. So we have to do 2 different problems. So we got 30 grams of N2 and 45 grams of H2. So for every 28 grams of N2, we form 1 mole of N2. For every one mole of N2, we form 2 moles of ammonia. We're on the mole train. All right, and we're done because I just asked for how many moles of ammonia are produced. So H2, every 2 grams of H2, we get 1 mole of H2. By now, you could probably recognize which one's limiting. For every 1 mole of H2, we produce, not for every 1 mole. For every 3 moles of H2, we produce 2 moles. Oh my gosh. Yeah. What am I doing? For every 3 moles of H2, we get 2 moles of NH3. So 45 times 2, divide that by 2 times 3, gives us 15 moles of NH3. And then let's do the top one. 30 times 2 divided by 28 gives us 2.14 moles of NH3. So which one's limiting? N2, because we produced less moles of our product. So our correct answer is 2.14 moles of ammonia are produced. All right, 2 more problems. How many grams of ammonia are produced from 40 grams of hydrogen gas with excess nitrogen? So excess nitrogen, oh my gosh, Mr. B, thank you so much for your help. Makes it so much easier. I'm honestly just thinking myself at this point, I'm exhausted. So we got 40 grams of H2. For every 2 grams of H2, we produce 1 mole of H2. And for every 3 moles of H2, we produce 2 moles of ammonia. And for every 1 mole of NH3, we form 17 grams of NH3. So 40 times 2 times 17, I'm doing all the numerators first, dividing it by 2 times 3, which gives us 226.67 grams of NH3. All right, last one. How many moles of H2 and N2 would be produced from 250 grams of ammonia? So how many moles of N2 and H2 would be produced from 250 grams of ammonia? So you know what? That's 2 different problems. So 250 grams of NH3, 250 grams of NH3, boom, boom, boom. For every 17 grams of ammonia, we get 1 mole of NH3. Remember, we always got to get on the mole train to be able to Stoich over. Okay, just doing them simultaneously. All right, and for every 2 moles of NH3, we form, oh, wait. Oh, right, we're going to H2 and N2 individually. For every 2 moles of NH3, we form 1 mole of N2, and we form 3 moles of H2. Equals, because we're done. We're just going to how many moles of N2 and H2 would be produced. So 250 times 1 divided by 17 divided by 2 gives us 7.35 moles of N2. So that's one answer. And then the second answer is 250 times 3 divided by 17 times 2, which gives us 22.06 moles of H2. All right, so I said both, not either one. So this is our answer, both of these. Okay, so hopefully that was a pretty exhaustive review, but hopefully that was enough to kind of help you along with all these practice problems. Again, I really recommend if you had any trouble with this, go back, re-watch a problem, see if you understand each of the steps along the way. By now, we should be pretty comfortable with dimensional analysis, so canceling units out and trying to convert from one unit to another. Now, I'll be completely honest, your test is not going to be nearly this challenging, especially compared to some of these challenging problems. But if you're able to do this entire review, you are in a really, really good spot for the test coming up, okay? So just be careful to be able to recognize limiting reactant problems versus excess reactant problems, as well as be comfortable with new information. So if I gave you maybe like density, or if I gave you moles instead of grams, I want you to be comfortable with using all different units, not just memorizing a simple procedure, okay? All right, that's it, everybody. I hope you have a great rest of your day. Please be sure to email me or ask any questions. I will be happy to answer them or give you some more practice problems, okay? You guys got this. I'll see you tomorrow. Bye-bye.